Right. Hi, everybody. Good morning, good afternoon, or good evening, whenever you're watching this. We're moving swiftly on today, and we'll move on to velocity time graphs, not to be confused with distance time graphs, which we saw previously. The main things we're going to talk about, or some of the main points that we'll cover, are above my head. Velocity time graphs help you to find out acceleration. And acceleration is defined as change in velocity divided by change in time. Or another way of looking at it is acceleration equals your final velocity minus your starting velocity divided by the time it took. In symbols, the same thing, A equals V minus U over T, where A stands for acceleration, V is final velocity, U is starting velocity, and T is time taken. And finally, it's very important you understand that the unit of acceleration, and it's the meter per second, which we usually refer to as the meter per second squared. Okay, so just before I move on, probably one of the biggest mistakes I see in IGCSE Physics every year is confusion between what a velocity time graph is showing and what a distance time graph is showing. It's very important you don't confuse the two of them. And I know that because I remember getting confused by it when I did my GCSEs many moons ago. So let me begin by showing you a distance time graph. This is the same distance time graph I put on the previous video. And you should remember what each of these different shaped lines represents. On a distance time graph, a diagonal line like this represents constant speed, or maybe I should say constant velocity. A horizontal flat line represents no change in velocity, so therefore the object is not moving. An upward sloping curve represents acceleration. A downward sloping curve represents deceleration. And at the end there I have another section where the object is not moving. Okay, that's a distance time graph. It's very important that when you see a velocity time graph, you might see the same types of shapes, but they'll mean something different, because we're going to change the y-axis from distance in meters to velocity in meters per second. By the way, just before I move on, at this stage you should remember that there is a difference between the term velocity and speed in physics. We tend to use them interchangeably in the English language, but in physics we talk about velocity when an object has a fixed direction, and we talk about speed when the object is just moving around randomly and it doesn't have a fixed direction. Velocity is a vector, speed is a scalar. V for velocity, V for vector, and S for speed, and S for scalar. Okay, so this is a velocity time graph. To make it obvious, I've changed the colour of the line, and obviously up here I've changed the y-axis. The y-axis now represents velocity in meters per second rather than distance in meters. Very important, whenever you see a graph question like this, always check what it says on the y-axis first, please, and don't fall into the trap of getting the two things mixed up. Okay, you might want to pause it there and just take a minute. I want you to think about what you think is happening at each of these stages. I think there's 6 stages on this journey, before I actually tell you what it means. Have a think about what each of those lines might mean. Okay, so I can see that there's, I think, 6 stages. There's a first stage with a upward sloping diagonal line. Now on a velocity time graph, what that means is velocity is increasing as time increases. So therefore this represents an increase in velocity, or we could say the object is accelerating. Its velocity is increasing. The next stage is a flat line. This flat line, well, its velocity is not changing, but time is still moving forward. So therefore that represents a fixed constant velocity, in this case for 20 seconds. This upward sloping line again represents acceleration or increasing velocity. But before I talk about this, have a think about what that gradient might mean about this acceleration compared to the first section. We have a flat line again there. That represents constant speed again. A very steeply sloping upwards line, straight line, which again must represent acceleration. Again, constant speed, this time 60 meters per second. And the final section, well, I don't know if you worked it out. In a distance time graph, that kind of shape would represent return to the starting point, but that's not the case in a velocity time graph. Okay, that represents basically a decrease in velocity over time, which we could refer to as deceleration. Okay, that's the basics of the graph. I hope it makes sense. Let's look a little more carefully at the numbers that we can get from this graph. I think the easiest thing to look at first is those horizontal lines, which I already said represent constant speed. So this first one, I can see that that's a constant speed of 10 meters per second for 20 seconds. This second one is a constant speed of, constant velocity, I shouldn't use them interchangeably, a constant velocity of 30 meters per second for 10 seconds. And the final one is a higher velocity, a higher constant velocity of 60 meters per second for, looks like 30 seconds to me. Okay, that's easy. That's fairly straightforward horizontal line, as long as you don't confuse it with a distance time graph. Okay, let's look at the other sections now. So we can go first of all to this first part. It's an upward sloping line. I already said it represents increasing velocity or acceleration. Now you might have already worked out that if we can get a gradient from a distance time graph, we can also get a gradient from a velocity time graph, but it will mean something different in both cases. Okay, so let's give this some thought. So if I get my pen, I can say that for this section, gradient is change in the y-axis divided by change in the x-axis, just as we saw before for a distance time graph. But in this case, the change in the y-axis represents a change in velocity, and a change in the x-axis represents change in time. Now you can see from above my head, change in velocity over change in time represents acceleration. So this gradient, for the triangle I've drawn here with the blue dotted line, that gradient will give us the acceleration over that part of the journey. So therefore, the acceleration is, well, we can see that the finishing velocity here is 10 meters per second. Its starting velocity was 0 meters per second. And the change in time is, well, 20 seconds minus 0 seconds. 10 divided by 20 gives us an acceleration of 0.5 meters per second squared. Don't forget to use the correct units, please. Okay. Let's move on to the next section. So the next acceleration that we could calculate, again, from the gradient, well, this gradient, again, change in y-axis velocity divided by change in x-axis time. Okay, well that looks to me like the change in velocity is 30 meters per second. That's the finishing velocity minus the velocity it started at this point, 10, divided by the change in time. Well, I can see there it's 50 seconds minus 40 seconds. Okay, so that gradient or that acceleration therefore is equal to 30 minus 10, 20, divided by 50 minus 40, 10. 20 divided by 10 equals 2 meters per second squared. Okay, this one, gradient equals change in velocity divided by change in time, which in this case will be equal to 60 minus 30 divided by the change in time, 70 minus 60. Okay, that means the acceleration is 60 minus 30, which is 30, divided by 70 minus 60, 10. That acceleration is equal to 3 meters per second squared. Okay, I hope that made sense. You should be able to see that for the three slopes we saw, the gradient increased each time, and therefore our calculation of the value of acceleration increased each time. Okay, that leaves us this final triangle, or this final line at the end, which is a bit more tricky. So again, gradient is change in y divided by change in x. Okay, so my change in the y value is going to be my finishing velocity minus my starting velocity, and this is where it's a bit strange. Okay, my finishing velocity is, in this case, 0 meters per second, and my starting velocity is 60 meters per second, and the time it took, well, I can see there it's 20 seconds. Okay, so therefore, in this case, my acceleration equals 0 minus 60 is minus 60 divided by 20. I have an acceleration here of minus 3 meters per second squared. Now, you might think that's a bit strange, and you might think I've made a mistake. But acceleration can be positive and negative. And when you get negative acceleration, we could also call that deceleration. So I can say that between these 2 points, this object has an acceleration of minus 3 meters per second squared, or I can also say it is decelerating at plus 3 meters per second squared. Okay, I hope that made sense. I think I've got one more thing to show you before I finish this video. So we've talked about what the shapes mean. We've talked about what the gradients of those lines mean. One other thing that Cambridge wants you to know or remember for these kind of questions is that we can also get the total distance travelled, or the distance travelled for each section of the journey, from this graph as well. The trick here is that distance travelled is equal to the area underneath the graph. Okay, so to do that, we can take separate sections. We've got a section here, so I can calculate the distance travelled between this point and this point by finding the area underneath the graph between those 2 points. So therefore, the distance travelled here is the area under the graph. It's a triangle, and I know that the area of a triangle is half times the base multiplied by the height. So it's going to be half multiplied by 20, 0.5 times 20, multiplied by the height, which in this case is 10 meters per second. Okay. Half 20 times 10 is 10 times 10, which gives me a distance travelled of 100 meters. Only just between those 2 points. Okay, I can move on to the next part. Oh, that made sense, by the way. Move on to the next part. This part is a bit easier. The area under this part is no longer a triangle, it's a rectangle. So it's just going to be the base distance multiplied by the height distance. So I can see there that the distance travelled in this section is going to be, well, that's 20 seconds, the base, multiplied by the height, which is 10 seconds. 20 times 10 is 200 meters travelled. So it travelled further in the second section than it did in the first section, precisely twice as far. Okay, and I'll just do one more. Now this third section, This is a bit more tricky because here the area under the curve is not just that triangle, it's that triangle plus, in this case, the square underneath it. Okay, so we need to do two calculations for this distance. This distance, well, first of all, we can do the triangle. We get half of, well, 10 seconds, multiplied by the height of that triangle. I make that 20 meters per second. Half times 10 times 20 is 5 times 20, which is 100 meters. That represents the triangle only. And then I need to add on the area of the square, which is going to be 10 seconds multiplied by 10 meters per second, another 100 meters. So therefore, the total distance travelled in this section is 100 plus 100 meters, which equals 200 meters. Okay, now that's all the calculations I want to do here, because I want to leave the last part of this video for you to do the rest of the calculations. So my question for you is, do the calculation please and tell me what is the total distance travelled by this object from the start of its journey here to the end of its journey here. To do that, you need to calculate the area, the total area underneath the graph. So that's going to be all of these shapes joined together to give you that. You need to calculate an area for each one of those individual shapes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 shapes in total. And to make it easy, I've just made it triangles, rectangles, or squares. Okay, so I'll speak to you in the class, and the first question I'm going to ask you after you've watched this video is, what is your calculation for the total distance travelled by that moving object in this journey? Right, I hope that was helpful, everybody. Take care, and take care of yourselves and your family during this pandemic, and I will speak to you in our class. Okay, bye-bye.